Now let's start our chapter thermodynamics. So basically there are two important terms in this chapter. The first one is system and the second one is surrounding. So this system plus surrounding makes universe. Anything that is under observation, that is system, the rest of the things are surrounding. Another important term in this chapter is boundary. Now this boundary that basically separates system and surrounding, it can be rigid, non-rigid, conducting or non-conducting. Now let's understand the different types of systems. The first one, we have open system. In it, matter as well as energy that can be exchanged between system and surrounding. Second one is the closed system, in which there is only energy transfer. The third one is isolated system, neither the matter nor the energy transfers in this case. Now let's understand few important processes. The first one is isothermal process. Now this word iso, it represents same. So isothermal means the temperature is same, that is temperature is kept constant. The second one is isobaric. Now isobaric means pressure is kept constant. The third one is isochoric. It means volume is kept constant. This is very important, that is the adiabatic process. In it, heat is equal to 0 but the temperature changes. Now this one is very important to learn because it is different from isothermal process in which temperature was kept constant. Here temperature changes but heat is equal to 0. So this is our adiabatic process. Next important term is state functions. Now state function is a function whose value depend only on the initial as well as the final position. It does not depend upon the path. So in competitive exams we can be asked a question that which of the following is a state function. So examples are pressure, volume, temperature, internal energy, enthalpy, entropy as well as free energy. Now next important term is state variable. There are basically three important state variables: pressure, volume and temperature. Next important term is path function. Path function is a function whose values depends on the path, for example work done and heat. Next important term is intensive properties. Now these are those properties which remain unchanged when the system is subdivided. They do not depend on the size or the mass of the matter. Now in competitive exams we can have a question that which of the following is a example of intensive property in exams like IIT-JEE mains or NEET. So the examples of intensive properties are temperature, pressure, refractive index, viscosity, density, surface tension, specific heat, freezing point, boiling point, EMF of the cell. This is very important example. Please remember that EMF of the cell is an example of intensive property. pH of the solution, mole fraction or molarity. Next important term is extensive properties. Those properties whose value depend on the quantity of the matter, they are termed as extensive property. Examples are mass, volume, heat capacity, internal energy, enthalpy, entropy and Gibbs free energy. Gibbs free energy is an important example of extensive property. Now this is a very important note that anything which is expressed per mole or per gram or per volume, that is intensive property. We can say that extensive property, if it is divided by extensive property, it becomes a intensive property. For example, let us consider mole fraction. Now, mole fraction is basically moles of anything divided by total number of moles. As mole is a extensive property, so extensive divided by extensive becomes a intensive property, that is mole fraction. Similarly, molar volume and molar heat capacity, these are examples of intensive properties. Now, please remember that force is a extensive property and pressure is a intensive property. We know that pressure is equal to force upon area. So, this becomes a intensive property. This is a very important point to note, that extensive properties, they are additive in nature, but intensive properties, they are not additive in nature. So, please remember that intensive properties are not additive in nature. Now, moving on to our next term in this chapter, that is a cyclic process. What do you understand by a cyclic process? Whenever a system that undergoes any changes, but ultimately it reaches to its initial state. So, in that case we say that our delta U, now delta U is nothing but change in internal energy. In some books it is also written as delta E. So, delta U in the case of cyclic process, that becomes equal to 0. So, this is a very important point to remember, that in case of a cyclic process, our delta U value is equal to 0 and delta H, that is the change in enthalpy, that is also equal to 0. Now, these are few sign conventions that must be remembered while dealing with the numericals of thermochemistry or thermodynamics in chemistry. If work is done on the system, that is a contraction work, it is considered as a positive. If work is done by the system, that is expansion work, it is considered as negative. If heat is absorbed by the system, we say that is an example of endothermic process. So, its value is considered to be positive. If heat is released by the system, we see that is a exothermic process and its value is considered to be negative. Now, these sign conventions are very important while dealing with the numericals of thermodynamics. Now, let us derive an important conclusion that work done is a product of pressure and volume. Let us consider a simple case. We are applying a pressure on this piston and this piston is moving at a distance dl with the area of cross section A. So, we know that pressure is equal to force upon area and work done is equal to force multiplied by displacement. So, displacement in this case is dl, there is a small change in the distance. So, force will be equal to pressure into area. Let us replace the value of force here. So, work done will be equal to pressure multiplied by area multiplied by distance, that is dl. We know that area multiplied by distance, that is nothing but volume. So, we can say that work done is equal to pressure multiplied by dV, that is change in volume. So, integrating both these things, integration of work done will be equal to W. We are integrating PdV from volume V1 to V2. So, in the case of expansion, our V2 will be greater than V1. So, using the formulas, we know that it is upper limit minus lower limit. So, P will be equal to V2 minus V1, that is P delta V, or I can say that work done is equal to negative of P external delta V in the case of expansion, or V2 is greater than V1, In the case of contraction, our V2 is less than V1. Now let us consider these graphs. These are very important. These are the graphs we have plotted between pressure and volume. In the y axis we have taken pressure, on the x axis we have taken volume. So let us consider this first line, that is isobaric. So here pressure is kept constant, but the volume is changing. So this line is representing isobaric. Let us consider this green line. Here the value of V is same, but pressure is changing. So if V is constant, that is isochoric, and these two lines represents the isothermic as well as adiabatic process. Adiabatic graph is little bit steep than isothermic. So if we consider the area covered under this pressure volume graph, so that is P multiplied by V, this is nothing but work done. So area covered under this pressure volume curve will give us the value of work done. So let us consider the area covered under isothermic curve. This area we can clearly see is greater than the area covered under adiabatic process. So we can conclude that work done in the case of isothermal process is greater than the work done in the case of adiabatic process. This is a very important point for competitive exams. Now let us consider these few graphs. These are pressure volume curves. The first one is an example of cyclic process. Now we are moving from this point, we went there, then downwards, then returned back to the initial stage. So this is the cyclic curve. But the second one is not a example of a cyclic curve. We have moved there, here, but we haven't returned back, but this is our journey. So this is not the initial position. So this is an example of non-cyclic work. Now these two graphs are very important. Now first one is we are moving from here, that is we are moving from right to left. So volume in this case will be decreasing. So if you are decreasing the volume, that means you are contracting the system. So this graph is represent contraction work. Now the second, we are moving from here to here or from left to right, the volume is increasing. So this is an example of work done of expansion. Now let us try to understand if we are able to answer these two graphs, whether the work done covered under these graphs is positive or negative. Now consider them one by one. First of all, let us consider the upper line. We are moving from right to left. So if we are moving from right to left, that means we are decreasing the volume. That is an example of contraction. So we know that second line is we are moving from here to here, that is from left to right, we are increasing the volume, that is an example of expansion. So area covered under contraction curve is basically greater as compared to the area covered under expansion curve. So the overall answer will be the contraction work. So work done in the case of contraction is taken as positive, while the work done in the case of expansion is taken as a negative. So overall, as the area of contraction curve is greater than the area of expansion work, so net result is positive. So the value of work done in this graph will be positive. Now let us consider the second graph. Upper line, we are going from left to right. So we are increasing the volume, that is expansion work. we know that it is negative. The second line is we are moving from right to left. So, volume is decreasing. So, that is an example of contraction, that is positive work. So, the area covered in expansion curve is basically greater as compared to the area covered in contraction work. So, the net resultant will be negative. So, the area covered under this graph will be negative. These two graphs are very important for entrance exams like IIT-JEE and NEET. Now, let us drive an important expression. This is important for class 11 students in their school exams also. Work done in isothermal reversible expansion of an ideal gas. Let us drive this equation. We know that work done is minus P external dV. Now, for reversible expansion, P external is equal to P internal minus change in that small change in pressure. So, we can replace the value of P external here. So, we can write that work done is basically equal to minus of P internal minus dP into dV. Now, we know that product of two small changes, we can neglect this because this will give us the value even more smaller. I have mentioned here that dP into dV can be considered as negligible. So, I can rewrite the term as W is equal to minus P internal dV, integrating both sides from V1 to V2. So, we know that for ideal gas, from the ideal gas equation, PV is equal to nRT. So, I can write that P is equal to nRT by V. So, I can write that P internal is basically equal to nRT by V. So, I can replace this P internal in this equation. So, work done will be equal to negative of integration of nRT by V dV from V1 to V2. So, we know that dx by x, integration of dx by x is nothing but ln of x. So, here we will have ln of v, as we know that the formula is upper limit minus lower limit, and in the lns or logs the subtraction makes them dividing with each other. That is, the ln of a minus ln of b will be equal to ln of a divided by b. So, here we will have minus nRT ln of V2 by V1. So, we know that ln is equal to 2.303 of log. So, I can replace this value, that W is equal to minus of 2.303 nRT log of V2 by V1. Now, going back to the states of matter, we have Boyle's law, which says that P1 V1 is equal to P2 V2. So, I can rewrite V2 by V1 as P1 by P2. So, replacing this with the V2 by V1 in this equation, we conclude that work done is equal to minus of 2.303 nRT log of V2 by V1 in the case of isothermal reversible expansion of an ideal gas, or it is equal to minus of 2.303 nRT log of P1 by P2. These two are very important formulas for school exams as well as for competitive exams like IIT-JEE mains and NEET. Now, please remember two important points, that work done in the case of reversible process, that is greater than irreversible process, and work done in the case of reversible is considered to be the maximum work done. These are important for objective point of view. These 2 points can be asked in objective questions. Now, let us consider an example of a free expansion of an ideal gas. We are doing the expansion against the vacuum. So, free expansion means we are not applying any pressure. So, the P external is equal to 0 we know that W is equal to minus of P external delta V, as the value of P external in this case is 0. So, our W will be equal to 0. So, please remember that work done in the case of free expansion of an ideal gas for reversible or irreversible process is taken as 0. Now, this is the case of free expansion. This is important to note. Now, let us understand the basic laws of thermodynamics, going to our first law of thermodynamics. Now, it basically states that energy is neither created nor destroyed, although it can be converted from one form to another. That is, energy of an isolated system is constant, or the total energy of the universe is constant. Mathematically, this law can be represented as delta U is equal to Q plus W. Q here is heat absorbed, while W is the work done, and delta U is the change in the internal energy. So, this is our first law of thermodynamics, that is delta U is equal to Q plus W. We know that W is equal to negative of P external delta V. So, I can rewrite this as delta U is equal to Q minus P delta V, or Q is equal to delta U plus delta V. Now, let us come to few results from first law of thermodynamics. Our first case is a case of free expansion. Now, we know that in the case of free expansion, the P external is equal to 0. So, our W, that is equal to minus of P external delta V, as P external is equal to 0. So, W becomes equal to 0. So, we know that according to the first law of thermodynamics, delta U is equal to Q plus W, as W is 0 in this case. So, our delta U becomes equal to Q, that is the change in the internal energy in the case of free expansion is nothing but heat absorbed, that is equal to Q. This is very important for numericals. Now, let us consider the second case, that is the isothermal free expansion. We have included a word, that is isothermal. Now, before going to the result, first understand this, that internal energy of an ideal gas is a function of temperature. This is a very important point, and this should be kept in mind while dealing with the numericals in thermodynamics. So, that is a isothermal change, your temperature is constant. So, delta U becomes equal to 0. This is very important point. In the case of isothermal processes, your delta U, that is the change in internal energy, becomes equal to 0, as this is a function of temperature. So, if it is free expansion, so P external will also be equal to 0. So, W will become equal to 0, because W is equal to negative of P external delta V. So, first law of thermodynamics states that delta U is equal to Q plus W, as delta U is equal to 0, W is equal to 0, that means our Q will be equal to 0 also. So, please remember that in the case of isothermal free expansion, our internal energy change delta U is also equal to 0, our work done is also equal to 0, and our heat absorbed is also equal to 0. Now, the third one is very important, that is adiabatic process. This is very important for entrance exams. Adiabatic process, we have already done it, that for adiabatic process the heat change, that is Q is equal to 0. So, according to the first law of thermodynamics, delta U is equal to Q plus W. So, in this case Q is equal to 0, that means our delta U will be equal to W. Now when we will go further deep into this chapter, we will study a formula CV, that is heat capacity at a constant volume. That CV is basically equal to delta U by delta T. So I can say that delta U is equal to CV delta T. So we know that delta U is equal to W in the case of adiabatic process. So I can replace the value of delta U here. So work done in the case of adiabatic process is equal to CV delta T. This is a very important formula for competitive exams like IIT-JEE and NEET. Work done in the case of adiabatic process is CV delta T. Now let us do two important terms. The first one is QV and the second one is QP. Now what are these QV and QP? QV is basically equal to delta U and that is equal to heat absorbed or evolved at a constant volume. QP is represented as delta H. This is the enthalpy change of a system, which is equal to heat absorbed or evolved by the system at constant pressure. Now there is an important term, that is enthalpy. Enthalpy is equal to H and that is equal to U plus PV. So if we are changing this, so delta H will be equal to delta U plus P delta V. We know that formula for delta AB is equal to delta A into B plus B into delta A. So I can say that delta PV is equal to P delta V plus V delta P. So at a constant pressure, our delta P is equal to 0. So this term V delta P becomes equal to 0 in this case. So we are only left with the delta H is equal to delta U plus P delta V, which is generally mentioned in your books, that delta U is equal to delta U plus P delta V, but remember that the actual formula is delta U is equal to delta U plus P delta V plus V delta P. Now we know that PV is equal to nRT, so I can replace it as P delta V is equal to delta NGRT. So I can say that delta H is equal to delta U plus delta NGRT. So what is delta Ng here? That is number of moles of product minus number of moles of reactant. Now this is important to learn that here we are only considering the moles of gases. This is a very important point. So I can replace this delta H by QP and delta U by QV. So I can rewrite the formula as QP is equal to QV plus delta NGRT, again a very important formula for numericals. Now let us consider the conditions under which our delta H can be equal to delta U. We know that delta H is equal to delta U plus delta NGRT. Now for delta H to be equal to delta U, this delta NGRT should be equal to 0. Now how this term can be equal to 0? Let us understand this. First, delta Ng is equal to Np minus Nr. That means if Np and Nr is equal to same, if both the moles of product and reactant they are same, our delta Ng will be equal to 0. So delta NGRT term will be equal to 0. So naturally we are only left with the delta U is equal to delta H. If this term becomes equal to 0, and we also know that delta NGRT is equal to nothing but PV or work done. So if P external is equal to 0, work done becomes equal to 0 and this delta NGRT becomes equal to 0. So second thing is P external can be equal to 0. In that case delta H is equal to U. Similarly, if delta V is equal to 0, in that case P delta V becomes equal to 0. So again we are left with the delta H is equal to delta U. Now let us consider the another case if delta H is greater than delta U. Now for that to occur, our delta Ng should be equal to positive. This happens in the case if number of moles of product are greater than number of moles of reactant. So, we can have the result that delta H is greater than delta U. Another case is if delta H is less than delta U. This can happen if delta Ng becomes equal to negative. This only happens if number of moles of product are lesser than number of moles of reactants. Then we can have delta H is less than delta U. Now, we know that work done is equal to pressure into volume. So, in numericals the units of pressure are generally expressed in atmosphere and volume is in liter, but the work done is in joules. So, what is the relation between atmosphere, liter and joule? So, 1 atm liter is equal to 101.325 joule. This is very important for numericals, because generally in numericals in competitive exams work done is asked in joules. If it is in 1 bar liter, then it is equal to 100 joules. If QP or QV they are in calories, then R is considered to be 1.987 or approximately 2 calories per degree mole. If both the terms they are in joules, then R is equal to 8.314 joule per Kelvin per mole. If they are in kilojoules, then R is considered to be 0.008314. If they are in kilocalories, then R is equal to 0.002. Now, let us understand the few important terms in this chapter. The first one is the heat capacity, that is very important. Now, heat capacity is basically the amount of the heat that is absorbed or required to raise the temperature of any given object or amount of the object by 1 degree Celsius. So, we write it as Q is directly proportional to change in the temperature, and directly proportional sign can be replaced by C. So, Q is equal to C delta T. Here C is the heat capacity. So, I can write C is equal to Q by delta T. So, we can rewrite as a heat capacity at a constant volume, that is CV, is equal to QV by delta T, and QV we know that it is equal to delta U. So, CV becomes equal to delta U by delta T. The second is heat capacity at a constant pressure. This is Cp. Cp becomes equal to Qp by delta T, and Qp we know that it is equal to delta H. So, Cp becomes equal to delta H by delta T. Now, let us derive an important expression. We know that delta H is equal to delta U plus delta NGRT. Dividing both these sides by delta T, we are left with the delta H by delta T is equal to delta U by delta T plus delta NGRT by delta T. We know that delta H by delta T is nothing but equal to Cp, and delta U by delta T is nothing but equal to Cv plus Nr. Now, Cp is equal to Cv plus Nr. This relation is termed as a Mayer's relation. If the value of number of moles N is equal to 1, then Cp minus Cv is equal to R. We can say that Cp is greater than Cv. Next important term is atomicity, that is represented by gamma. It is equal to Cp by Cv. So, atomicity gamma, that is equal to Cp divided by Cv. Let us understand the second important term, that is the specific heat. Specific heat, it is the amount of the heat required to raise the temperature of 1 gram of substance by 1 degree Celsius. It is equal to heat capacity divided by mass of the substance. So, Q by delta T into M, we know that heat capacity is equal to Q by delta T, and this should be equal to specific heat multiplied by the mass of the substance. So, I can say Q is equal to M into specific heat into delta T. This is a very important formula again for numericals that are asked in entrance exams like IIT-JEE or NEET. Now please remember these two important points, that is specific heat, it depends upon the material of the object. For water, if it is in liquid state, it is 4.179 joules, and if it is in solid state, it is equal to 2.03 joules. Next important term is molar heat capacity. Now it is the amount of the heat that is required to increase the temperature of 1 mole of the substance by 1 degree Celsius. So it is represented as a molar heat capacity is equal to heat capacity divided by number of the moles. So Cm, that is representing the molar heat capacity, becomes equal to Q by delta T divided by number of moles. So number of moles is nothing but equal to mass of the substance divided by molar mass. We can replace the value of N. So our formula becomes Cm is equal to Q by delta T into capital M by small m. So I can say this Q by delta T into M is nothing but C. So molar heat capacity is equal to C multiplied by capital M. This is important for numericals. We are replacing Q by delta T into M by C. So Cm is equal to C multiplied by capital M. Let us consider this numerical. A piece of aluminium that is weighing 3 gram, it requires 5.4 joule of heat to raise the temperature from 298 Kelvin to 300 Kelvin. Calculate the following. The first term is to calculate the heat capacity. The second is to calculate the specific heat capacity, and the third one is to calculate the molar heat capacity. Now let us start with the calculation of heat capacity. We know that heat capacity is equal to Q by delta T. So Q in this numerical, that is heat absorbed, is given as 5.4 joule, while delta T, that is change in temperature, that will be equal to 300 minus 298, that is 2 Kelvin. So it is 5.4 divided by 2, this is equal to 2.7 joule per Kelvin. That is the value of heat capacity. Now the second term asked in this numerical is specific heat. We know that specific heat capacity is equal to Q by delta T into M, that is the mass of the substance. In this numerical, mass of aluminium is given 3 grams. So this is equal to 5.4 divided by 2 into 3, that is 0.9 joule per gram per Kelvin. So our specific heat capacity has been calculated. Now the third term is molar heat capacity. Now molar heat capacity is equal to Q by delta T into number of moles, that is N. We know that N is equal to given mass upon molar mass. So molar mass in this numerical, we are given aluminium here. So we know that molar mass of aluminium or atomic mass of aluminium is equal to 27. So this is equal to 24.3 joule per mole per Kelvin. So please remember that heat capacity is in joule per Kelvin, specific heat capacity is in joule per gram per Kelvin, while molar heat capacity is in joule per mole per Kelvin.